Such kind of situation is known as slender body, or it's a very long, where the flow is almost unidirectional, because V infinity will gradually goes to what? V infinity will gradually approaches to 0, because if this term will delta by L equal to 0, U into delta by L is equal to 0. So V infinity equal to 0 means the flow is unidirectional. Those kind of thing is known as the slender body, right? Let's come to the scaling analysis from the y momentum equation. This is my y momentum equation. Just in the same notion, what I did the scaling analysis. Here the tilde symbol represents the order of magnitude. I put it u infinity, right? Delta v, I put it v infinity minus 0 over what distance? Delta x distance. Delta x is nothing but L, right? Here v is there. V I approximated by v infinity. Delta v is nothing but v infinity minus 0, that is again v infinity, divided by delta y. Delta y how much? Thickness of the boundary layer, that is the delta, this small delta, right? Then there is the unknown term over here, the pressure gradient. We don't know what is the pressure. From the dimensional analysis, we can found delta v is same order of magnitude from the same, it is the same dimension as a rho into u infinity square. This is purely dimensional analysis. Even if you have solved earlier the Bernoulli equation, you can see that they are almost same, dimensionally same, right? We'll just, this is approximation, we'll put it, let's finally we'll saw this, if this approximation is correct or not. Okay, let's substitute delta p is the same order as rho u infinity square. This is some purely from the dimensional analysis. Finally we'll see what is the physical meaning of substitution, right? So then put delta p is how much? Rho u infinity square, right? Then this rho and the rho in the denominator that cancels each other. This is something minus I am not much interested, because here I am interested for order of magnitude analysis. Okay, this u infinity square in the top, delta y is nothing but minus small delta, right? Then there is another two terms in the diffusion, right? So one is nu times v infinity times delta x square, then this will become as L square. One is delta y square, this will come as delta square. Now for the slender body, okay, means having a body having a long length, right? What you will see. The boundary layer thickness delta is very small compared to the length of the plate, right? In that case, what we can do, we can assume, okay, the delta less than small l, 1 delta square by x square also less than delta square by y square. If there is a big term in the denominator, means that term is altogether approaching 0, right? Compared to this one. This one is a small, this one is a big. If there is a big number in the denominator, means the whole term after division is neglect compared to other term, right? So then what will happen? From the mass continuity equation, here there is an unknown v infinity. We don't know the value of the v infinity. To find the v infinity, what we did? We have solved the mass continuity equation over here. We found some functional form of the v infinity in terms of u infinity delta by l. So that functional form of the v infinity will do the substitution over here in terms of the v. Now everything in terms of what? L is a known quantity. Delta is a boundary layer thickness I need to know. U infinity is the free stream velocity. So now everything on my y momentum equation falls down to a condition where only the unknown terms is my boundary layer thickness, the rest things are known. Let's see what next. Okay, to find out, again doing the scaling analysis, we have a 4 term in the boundary layer equation. Let's find out which term are important, which term are not important. How to do order of magnitude analysis? First, divide each term with respect to other term to see what is their strength. To do that, let's first find out the ratio of inertia terms to pressure gradient term. This term represents my pressure gradient. This is my inertia. This is my viscous term. So once we divide the inertia to pressure gradient term, then we will get what? The term will represent some magnitude delta by L to the square. And what we will find, for a slender body, delta by L term is very small. The square of a small term is also small. This physically mathematically this approaches to 0. So this term is 0, means the inertia term is quite negligible compared to the pressure gradient term. So in this y momentum equation, we can neglect inertia because this is a less magnitude compared to the pressure gradient. Similarly, let's compare the magnitude of the pressure gradient term and the viscous distribution term. Okay, to do that, then divide the viscous force with the pressure gradient term force, right? The viscous force nu u infinity by delta L, this is the pressure gradient force. If you divide, you will get something nu, okay, divided by u infinity L, right? Altogether this will give you a thing 1 by Reynolds number, to the means based on the definition L, means total length of the plate. I have defined the Reynolds number. There is a lot of different definition of the Reynolds number. Here my characteristics length equals to length of the plate, that's why Reynolds number to the power n. So what will happen when you have a very high Reynolds number flow, 1000, 10,000 kind of flow in the laminar zone itself, even if 3000, 1 by 1000, this is again a negligible quantity, approaches to 0, right? So means the viscous force has negligible magnitude compared to the pressure gradient. So in this equation, we can neglect inertia, we can neglect viscous, whatever the remaining term, only the pressure gradient term will remain. So if that means the pressure gradient term in the Navier-Stokes equation, y momentum equation, should be equals to 0, because other terms are almost not of any significant magnitude. If the pressure del P by del Y term, this is the pressure gradient term, equals to 0 means what? My pressure is not a function of Y, pressure may be a function of X, but pressure is not a function of Y. The pressure is not a function of Y means, physically what is telling, within the boundary layer, if I move along Y direction here, my pressure is not changing. Pressure is not in the function of Y. So the pressure within the boundary layer is somehow constant, and this pressure is provided by the free stream or the core region or the bulk fluid. The total pressure on the boundary layer is provided. Pressure is not 0. The pressure gradient is 0. Means here to here pressure remains same, right? And that pressure is provided by the free stream or the bulk fluid over here. The free stream fluid provides the bulk pressure on the boundary layer. Inside the boundary layer, the pressure gradient is 0 on the Y direction, right? This is my Y momentum equation. I got it over. So there is no pressure variation in the Y direction of boundary layer. Pressure is impressed on the boundary layer by the outer flow of the bulk fluid. Let's come to the scaling analysis of the Y momentum equation. So this is the X momentum equation. By mistake, this has written as a Y momentum. This is X momentum equation actually. Okay, sorry, apology for the typos. So this is my X momentum equation in terms of the U. Just like Y momentum equation, what you do? Just do the substitution. U in terms of U infinity, delta U by delta X, you put U infinity minus 0, that is U infinity. So U infinity square in the delta X will be replaced by the L, because L minus 0. If you do this substitution and we have a functional form of V infinity in terms of U, delta and L, if you substitute all those things, right? And the pressure, already we have a find, delta P is nothing but rho U square, right? So if you put all those things, then we have find, okay, the functional definition, okay, of the pressure, okay, what the delta P by delta X, okay, if you put over all those things, okay, so if you, after putting all those things, you will find delta P by delta X is nothing but del P by del X. This should be ordinary differential equation, right? Now this is not a partial differential equation. The partial differential equation del P by del X, this is a typo. This should be d by dx, means this is boils down to ordinary differential equation, because my pressure is nowhere the function of y, my pressure is only the function of x. So my partial differential equation stands if it is a pressure is a function of y and x, then this partial differential equation works. Otherwise this partial differential equation boils down to the thing ordinary differential equation, dp infinity by dx, right? So p infinity what? We know that there is no pressure variation inside the boundary layer. The pressure in the boundary layer is provided by bulk fluid. So P infinity is the pressure in the free stream of flow. In the Bernoulli's equation, even if you assume the free stream of flow is what? This is one-dimensional, irrotational, incompressible, inviscid flow kind of thing, where Bernoulli's equation is applicable. What Bernoulli's equation is telling? It is again conservation of mechanical energy equation for streamlined one-dimensional irrotational flow. If you come over here we something assume first over here, delta P is equal to rho U infinity square. From where? From the pure dimensional analysis. Here, after putting the Bernoulli's equation, we can find that our assumption was correct. P infinity plus half into rho into infinity square, it should be constant, right? Because from the Bernoulli's equation, then del P by del X, if you do it, then it will be give some in terms of y and there some derivation with respect to the constant that will approaches to 0, right? So this is my Navier-Stokes equation. Let's come how to simplify it. Then my boundary layer equation boils down to the following form, right? First, I have the mass continuity equation as it is in the Navier-Stokes equation. In the x momentum equation, my partial differential equation with respect to x in the pressure gradient term, that boils down my ordinary differential equation. This P infinity is the bulk pressure provided by the free stream fluid, right? U is my velocity in the boundary layer, and in the y momentum equation, I found del P by del y equals to 0. So for the simplicity, I derived the equation over the flat plate. In general, this boundary layer equation is valid for any surface, right? If it is a curvature surface, it's not like that xy direction is just like I have a static x coordinate or y coordinate. With respect to the plate also, I can change my x coordinate, just like here tangential component represents x, the vertical component represents y. Here the coordinate also changes. Such kind of coordinate system is known as streamline coordinate system, where x represents my streamwise direction or for y represents my streamwise direction, right? So this is my boundary layer equation, right? So then we'll assume for the slender body. What is slender body? Delta by L less than 1. Let's come to the solution, right? This is my boundary layer. Okay, let's come to the boundary layer condition for the flow over a flat plate. So we'll not initially go for the condition like what will happen when the boundary layer is flow over the curved body or something. For the simplicity, let's assume the flow over a flat plate kind of thing. When it is a flat plate, when the flow is hitting, what is the situation over there, right? Let's come. Okay, this is my boundary layer flow over a flat plate, right? Without any boundary layer separation means I am not going to any turbulent or the transition zone, right? Let's do again the order of analysis, right? In this equation, just put the order of analysis for x momentum equation. In the x momentum equation, we found out which term is important. Here we found out the pressure gradient term is not that important. From the Bernoulli equation, P infinity plus half rho u square is equal to constant, right? Del P infinity by del x is equal to, again you do it by chain rule, you do the differentiation rho u infinity d rho u infinity by dx equals to derivation of the constant equal to 0. As rho u infinity is a constant, this is no more varying with respect to x direction. This term is equal to 0, so del P infinity by dpx, this is also 0. So this term, pressure gradient term in the x momentum equation is essentially 0. There is no pressure is also not varying in the x direction also inside the boundary layer, right? So we have finally got the governing equation for the boundary layer, right? When there is no pressure gradient term in the x direction also, right? Now to do have a solution, let's do the same scale of order of magnitude analysis. U del u by del x, this is nothing but u infinity by L, because here u is equal to u infinity. Del u is nothing but u infinity, u infinity minus 0. Delta x is nothing but by distance from 0 to L, right? Similarly, v del u by del y, if you do the order of magnitude analysis, this will come u infinity square by L is some order of magnitude as u infinity by delta square, right? After doing the solution for this equation, right? Here we have a simplified form. Here someone may be questioned that plus of u infinity square by L, u infinity square by L, okay, there may be 2 u infinity square by L, but here we are not interested actually in the addition, rather we are interested to find out the order of magnitude analysis, means if the order of magnitude of both terms is same or not, okay. So delta square by L is equals to, we'll find, this is mu by u infinity after solving this equation algebraically, nothing. Then what is the our finding from this? We find out the thickness delta of the boundary layer at a length L. That is how much? After simplifying, we'll found out that is some constant C, proportionality constant C, times the Reynolds number to the power minus 0.5. Means what? This delta and what is this L? Suppose this plate is having a variable length from somewhere from 0, okay, to goes on increasing in this direction, maximum length is L, right? At any point here, for a particular x, we have a delta x. So what is that delta x value for a particular x, that we can get from that relation. Suppose at the full length of the plate we are measuring at the length L, what should be my final boundary layer thickness? That's represented by the Reynolds number derivation we get from the order of magnitude analysis over here, right? Yes, right? Although this theory is very simple, that gives us a very important relationship. First should be the thickness of the boundary layer, but that is not the end of the story, because as I told, the boundary layer theory is all of total developed to calculate the aerodynamic drag kind of thing, that the development of the aeroplane wings and all before the Second World War. The same thing in practice to calculate the aerodynamics of wing shape and all. So then the to develop the calculate the drag force, to develop the aero wing, the important factor is to calculate the wall shear. Wall shear is what? Wall shear is the shear force near the vicinity of the wall. This is nothing but mu del u by del y, right? This is at y is equal to 0. So mu del u is how much? From order of magnitude u infinity minus 0. Then what is the del y? This is nothing but at a particular x location. Del y is nothing but my thickness of that boundary layer minus 0, right? So then there is, just like you are doing the non-dimensionalization for any other quantity in fluid mechanics. So from the scaling and from dimensional analysis, we can non-dimensionalize the wall shear stress. That is called skin friction coefficient. When we divide the tau omega with rho u infinity square, that gives us a non-dimensional thing. So if you are measuring in millimeter, foot, centimeter or meter, that will be irrelevant, because when you are developing the wall shear stress, the unit matter in which unit you are measuring. But this non-dimensional coefficient, they are unitless. They are same irrespective of whatever the unit, SI unit or CGS unit, MKS unit, whatever unit you are following, right? CF equal to tau omega divided by half rho square. Then we have a functional notation for this skin wall shear stress. We can put it over, plot it over here. Then we can found the skin friction coefficient, that is nothing but these are same to my Reynolds number at a location x to the power minus 0.5. Means if I know my Reynolds number at a particular point, means if I know my x distance from at a particular point, I can have a skin friction assessment. Okay, because Reynolds number I know, u infinity I know, nu I know for the fluid. If I know the distance from the beginning, I can calculate the drag force. Imagine just it's a aerodynamic wing and the flow is hitting over it at a different position. The aerodynamic drag force is going to be different. If you know the position, now you can calculate the skin friction coefficient and aerodynamic drag by just integrating the skin friction over the entire surface, right? So that was the finding. Okay, so that simplify essentially derived from the simple approximation of the Prandtl, and that bring a whole revolution in the fluid mechanics before 1950. Before the numerical solution was available, based on this simplified version, lot of things are developed and designed, fluid dynamics, right? Again, the question is that to do the solution, we have assumed the order of magnitude or the simplified solution. But again, to get the exact value, what is the C value, this proportionality constant and all. Lot of students of Prandtl has a big legacy, just like von Karman, Bacillus, Nicorace, and all of the top scientists of those era. So they further carry out that legacy. They have developed a lot of methods, just like variable separable method. They call it similarity transform method. So this Bacillus developed a similarity transform method. Then von Karman developed a momentum integral method. Using different methods, they found more and more accurate and robust solution for this skin friction coefficient or the wall shear stress. That essentially was developed, required at that point of time to design the aeroplane and other aerodynamic structures, right? So these are the things. So boundary layer, in this lecture we have come across what is boundary layer theory, how the boundary layer theory is simplified, form of the Navier-Stokes equation, what is the solution, what is the requirement. This is some of the glimpse from the stretching or the similarity transform solution. Even if the boundary layer size is changing, the shape is not changing. If you look at the edge, the shape is remaining almost similar. So based upon that, they develop something called similarity transform solution, which is nothing but the variable separable method in the mathematics. So as time is not permitting, we will not go into detail other methods. So we can end the today's session over here.